In this lecture, we will explore how humans have studied the ocean over time. Ocean exploration is not just a history of travel. It is a history of curiosity, of observation, and of technology. Each major advance in ocean science occurred because humans developed new ways to observe parts of the ocean that were previously inaccessible. And I want to review those with you today. Humans began exploring the ocean long before oceanography existed as a science, and the earliest motivations were practical ones. One major driver was navigation and trade. The map of ancient Mediterranean trade routes shows how coastal seas served as early transportation networks. Civilizations depended on predictable routes to move goods and ideas, and that required detailed knowledge of coastlines, of the winds, of the weather, and of the currents. The second map, showing trade routes between China and Alexandria across the Indian River, highlights that ocean exploration was not limited to Europe. Long-distance trade connected Asia, Africa, and the Middle East, and sailors learned to use seasonal wind patterns such as monsoons to plan their voyages. Another motivation was food and resources, as fishing communities depended on the ocean for survival. And finally, curiosity and discovery emerged as people began asking questions about the ocean itself, how it worked, what lived in it, and how far it extended. These motivations led the groundwork for ocean exploration and eventually ocean science. Some of the earliest ocean explorers were seafaring cultures that developed sophisticated knowledge of the ocean without any modern technology. Perhaps the most skilled were the Polynesians. The image of the traditional Polynesian ocean-going vessel highlights that long-distance travel across the open ocean was possible using carefully designed boats and deep environmental knowledge. Polynesian navigators did not rely on instruments or written maps. Instead, they used oral knowledge passed down through generations. The second illustration, showing the dispersal of humans from Asia across the Pacific Islands, demonstrates just how remarkable this navigation was. Reaching increasingly distant islands required an understanding of ocean currents, prevailing winds, wave patterns, and the movement of stars. These voyages were intentional. They were not accidental. Together, these examples show that detailed ocean knowledge existed long before modern science or technology, and that ocean exploration was built on observation, memory, and experience. One of the earliest figures to approach the ocean scientifically was Aristotle, who lived from 384 to 322 BC. Aristotle is often considered the world's first scientist, and more specifically, the first marine biologist. What makes Aristotle especially important is not just that he described over 500 animal species, many of them marine, but how he did his work. At a time when most explanations of nature relied on mythology or philosophy, Aristotle used systematic observation. He carefully examined organisms, compared their structures and behaviors, and recorded what he actually saw. From these observations, Aristotle drew logical conclusions based on evidence rather than tradition or beliefs. This approach, using empirical observations to support explanations, was highly unusual for this time period and represents an early foundation of the scientific method. In this way, Aristotle's work marks a transition from storytelling about nature to actually studying nature through observations, which is a core principle of science and oceanography today. Alexander the Great, who lived in the 4th century BC, is important to ocean history not because he was a scientist, but because he supported and enabled scientific observation. He was tutored by Aristotle, and that influence shaped how he viewed the natural world. Historical accounts describe Alexander using a diving bell to observe underwater environments. You can see the diving bell in these two paintings from the time period. Perhaps he was the first person to do so. While some details may be exaggerated, the key point is clear. Humans were attempting to directly observe the underwater world more than 2,000 years ago. Alexander also supported scientific study by collecting and sending biological specimens to Aristotle. In this way, he represents an early link between exploration, technology, and scientific inquiry. Together, Aristotle and Alexander show that ocean science began not with modern instruments, but with curiosity, with observation, and with the desire to see beyond the surface. The age of exploration, spanning roughly the 15th to 17th centuries, marked a major expansion of long-distance ocean travel. During this period, European nations established global sea routes that connected continents for the first time. The illustration of the exploration ship represents the technological advances that made these voyages possible, including improved ship design and navigational tools. The world map showing early explorer routes highlights how ocean travel became truly global, linking Europe with Africa, Asia, and the Americas. These voyages dramatically expanded geographic knowledge of the ocean and the coastlines. However, it is important to recognize that this period of exploration was also closely tied to European expansion, colonization, and exploitation of both people and natural resources. From an oceanography perspective, the key takeaway is that this era greatly increased observations of winds, currents, and ocean conditions, even though exploration was driven primarily by economic and political goals rather than scientific ones. During the age of exploration, most ocean knowledge came from direct observations at the sea surface. Sailors carefully recorded winds, currents, and surface conditions because this information was essential for navigation and survival. Images of explorers on ship decks emphasize an important limitation. Everything they observed came from above the water. They could feel the waves, they could measure the wind, they could notice surface currents, but they had no way to study the deep ocean or what really lies underneath. As a result, coastlines were mapped first. The distorted world map illustrates how early maps captured the general shape of continents, but often misrepresented distances and ocean spaces. The open ocean itself remained largely unknown and poorly understood. The key takeaway is that early ocean exploration produced valuable surface knowledge, but for centuries the interior of the ocean was essentially inaccessible. One of the earliest methods used to measure ocean depth was the lead line, sometimes pronounced the lead line. It's a rope with a heavy lead weight attached to one end. Sailors lowered the line until it reached the sea floor and then measured how much rope had been left out. The diagram on the left shows markings along the rope indicating different fathoms, which was the traditional unit used to measure the depth at sea. 1 fathom is equal to 6 feet. This is roughly the span of a person's outstretched arms. This method worked in shallow coastal waters, but it was extremely limited. Lead lines were difficult to use in rough conditions, impractical in deep water, and often inaccurate. As a result, reliable depth measurements were rare, and the deep ocean remained largely unknown for centuries. The Challenger expedition, which took place from 1872 to 1876, is widely considered the beginning of modern oceanography. What made this expedition different from earlier voyages is that it was designed specifically for scientific research, not trade, not exploration, and not conquest, just for research. The image of the ship represents a research platform rather than an exploration vessel. Scientists on board collected water samples, they measured depth, they recorded temperatures, and documented marine life in a very systematic way. You can see the laboratory on the bottom right drawing on this slide. The map of Challenger's route is especially important. Rather than following coastlines or trade routes, the ship made intentional crossings of the Atlantic Ocean and then traveled around the globe. These routes were planned to collect data from the open ocean, not just from nearshore areas. This marks a shift from opportunistic observation to deliberate, hypothesis-driven data collection, which is why the Challenger expedition is considered the foundation of modern oceanography. Before the Challenger expedition, many scientists believed that the deep ocean was lifeless and relatively unimportant. Challenger's discoveries completely overturned that view. The sketches of organisms on this slide represent one of the expedition's most important findings. Life exists in the deep sea. Challenger collected organisms from depths where scientists had assumed conditions were too extreme for life. This fundamentally changed how we think about the limits of life on Earth. Challenger also discovered major features of the sea floor, including the Mid-Atlantic Ridge and the Marianas Trench. These findings revealed that the ocean floor is not flat or featureless, but instead is highly structured, an idea that would later become central to plate tectonics. The bottles you see here labeled foraminifera highlight another key contribution. Challenger systematically collected water samples, measured ocean chemistry, and gathered deep sea sediments. These data allowed scientists to begin comparing different parts of the ocean in a quantitative way. These samples also allowed for the discovery of thousands of species of plankton until not even known until now. Together, these discoveries transformed the ocean from a largely unknown space into a system that could be studied scientifically. Modern oceanography is defined by the tools we use to observe the ocean, many of which allow us to study regions that were once completely inaccessible. The image of a ship using echo sounding or sonar shows how scientists map the seafloor by sending sound waves toward the bottom and measuring how long they take to return. This technique has transformed our understanding of seafloor topography and ocean basins. The submersible image represents another major advance. Submersibles allow scientists to directly observe deep sea environments, collect samples, and study organisms in their natural habitat rather than relying only on surface measurements. The satellite image highlights how oceanography now operates at a global scale. Satellites measure sea surface height, temperature, and color, which helps scientists track currents, productivity, and large-scale ocean circulation. Autonomous instruments, such as drifting floats and underwater sensors, collect data continuously over long periods of time. And finally, I'm highlighting here the plans for an underwater research laboratory in the Florida Keys, which will allow scientists to live and work underwater for extended periods of time. This will allow for sustained observations and experimentation at depth. This underwater research lab is being built by Florida International University and will be open probably within the next few years. Together, these tools illustrate how modern oceanography combines direct observation, remote sensing, and long-term monitoring to study the ocean as a connected system. Ocean exploration remains essential because the ocean plays a central role in some of the most pressing challenges we face today. The image of the fishing vessel with its catch highlights resource management. Understanding where species live, how populations change, and how ecosystems function is critical for managing fisheries sustainably and avoiding overexploitation. The graph showing changes in carbon dioxide concentration and temperature over the last 800,000 years connects ocean exploration directly to climate change. Much of what we know about Earth's climate system comes from ocean data, including how the ocean absorbs heat and carbon dioxide and influences long-term climate patterns. The image of the deep sea floor with mineral nodules represents a growing frontier in environmental protection and exploration. As interest in deep-sea mining increases, scientific exploration is essential to understand these environments before human activities alter them. Together, these examples show that ocean exploration is not just about discovery, it is necessary for informed decision-making about climate, resources, and the future health of our planet. In the next lecture, we will continue this conversation about how we explore the oceans. We will focus specifically on bathymetry as a tool for mapping the seafloor. Bathymetry has transformed our understanding of ocean basins, plate boundaries, and deep ocean processes. It is a powerful example of how exploration and technology continue to shape the ocean science.